This is the screencast for section 9.2, example 1. We are going to work with Taylor series and we're going to construct this series. Now, a Taylor polynomial is a polynomial that we're going to design to be an approximation of a function using a series. You kind of have already seen this in section 9.1, but now we're going to have a different approach to creating this polynomial. Exploration 1 gives you an introduction on how to find these polynomials. Now the approach we're going to take is by making each derivative of the polynomial and the log or the function we're dealing with equal to each other. So if the first derivative of the polynomial equals the first derivative of the function, when you integrate, the actual terms of those functions will equal each other, the polynomial and the function we're dealing with. Same thing with the second derivative. If the second derivatives equal each other, if you integrate twice, the resulting polynomial and the function you're dealing with would equal each other. Now, of course, the more derivatives we go into this that equal each other, the more accurate our polynomial is going to be as an approximation of the function. Now, I know that's hard to picture right now. You'll have to bear with me. Example 1 is going to kind of go the long way. Example 2 is going to go the long way. And then finally, example 3 is going to be the shortcut way. So again, bear with me so that you can see first how this works and understand how it works, and then we'll do the shortcut way. Alright, so for example 1, we're going to approximate the function the natural log of 1 plus x by creating a polynomial. So we're going to construct this polynomial, which is a coefficient times x to the 0 plus another coefficient x to the first plus another coefficient x to the squared, and you get the idea. In this one, we're going to go all the way up to x to the 4th. That matches the behavior of the natural log of 1 plus x at x equals 0 through its first 4 derivatives. So we're not going to start matching the behavior out at x equals 1. We're going to start at the y-axis. Now, what that means is we're going to create a polynomial who at 0 equals the natural log of 0. Then the first derivative of the polynomial is going to equal the first derivative of the natural log function at 0, etc. So first step is setting p of 0 equal to f of 0. So in other words, our polynomial at 0 has to equal the function's value at 0. Which means the polynomial at 0 has to equal the natural log of 1 plus 0. Well, the natural log of 1 is 0. The polynomial evaluated at 0 would be, if I plugged in 0 for all those x's, all I had left was a sub 0. So a sub 0 equals 0. So that first coefficient is 0. Now we're going to take the first derivative of both sides. We want the first derivative of this polynomial we're creating to equal the first derivative of the function that we're trying to approximate, also at 0. Well, the first derivative of the natural log of 1 plus x is the natural log of 1 plus x prime evaluated at 0. The derivative of a sub 0 is 0. The derivative of a sub 1x is just a sub 1. The derivative of a sub 2x squared is now 2a sub 2x to the first. The derivative of a sub 3x cubed is 3a sub 3x squared, etc. And then the derivative of the natural log of 1 plus x is 1 over 1 plus x. Now we evaluate both of those at 0. Plug in 0 to both of those. On the left side, the polynomial leaves us with a sub 1. And the right side, the f prime evaluated at 0 is 1. So now a sub 1, that coefficient is going to be 1. Now I'm going to keep this pattern going for the second derivative, the third derivative, the fourth derivative, as many derivatives as I need to. Now this one's only asking for the fourth. So I set the second derivative of our polynomial equal to the second derivative of our log function. So that means I need to find the second derivative of that log function. I got the second derivative of the polynomial, so now the derivative of a sub 1 was 0. The derivative of 2a sub 2x is just going to be 2a sub 2. Now I have 3 times 2 times a sub 3 x to the first, and then 3 times 4 times a sub 4 x squared. Plug in 0 to both of those, and I get that a sub 2 equals negative 1. So the a sub 2 coefficient is going to be negative 1. Third derivative, same thing. Take the third derivative of both the polynomial and the log function. And so that I'm just doing continuing basically from the second derivative. And then I have to plug in 0 to both sides, and I get that a sub 3 is going to be 1/3. Now finally, the fourth derivative of the polynomial is just 24a sub 4. And then the fourth derivative of the natural log of 1 plus x is going to be -6 parentheses 1 plus x to the -4th. Plug in 0, solve for a sub 4, and I get a sub 4 equals -1/4. So now we can create this polynomial. We found all of the coefficients. A sub 0 we said was 0. A sub 1 we found over here was 1. A sub 2 is -1/2. Oops, I had that as -1. It should have been -1/2. I'll fix that in a second. A sub 3 is 1/3. And then finally, a sub 4 is -1/4. And then if I simplify, I get this polynomial. Well, in this polynomial is an approximation for the natural log of 1 plus x. So let's see that. I'm going to put in y1, the natural log of 1 plus x, in y2, the 4-term polynomial, and you can see there's this nice approximation, not everywhere, but around 0 especially, there's a nice approximation. It starts, you can see, to get a little bit different here, very different over here. That will have to do with the interval of convergence, -1 to 1. The now try problem number 1 says construct the fourth order Taylor polynomial at x equals 0 for the function. That means we're going to go up to the fourth derivative. It does not mean 4 terms, it means up to the fourth derivative, fourth order. Now, in the interest of saving time and working towards our more efficient method, I notice a pattern in example 1 in that p of 0 is a sub 0. P prime of 0 is a sub 1. P double prime of 0 was 2a sub 2, because you had that squared on the x, and then you took the first derivative that brought the 2 down, the second derivative brought the 1 down, and then there you go. The third derivative of p evaluated at 0 is now 6a cubed, the 2 times the 3, the cube from the x cubed that it originally had. The fourth derivative then is 2 times 3 times 4 because of the fourth derivative in the fourth exponent in the first derivative, the 3 exponent in the second derivative, and then the 2 exponent in the third derivative. And then this derivative would be an exponent of 1, so it didn't change anything. So now I've noticed all that. Now I don't need to do that work anymore. So I can find p of 0 equals f of 0. Well, that means a sub 0 equals 1. F of 0, square root of 1 plus 0 squared is 1. Now, p prime of 0 will equal f prime of 0. P prime of 0 I already know is a sub 1. Done. F prime of 0, the derivative here, don't forget the chain rule. Evaluate that at 0, and I get a sub 1 equals 0. The second derivative of the polynomial has to equal the second derivative of our function for this polynomial approximation. So p double prime of 0 is 2a a sub 2. And then this was a messy product rule, but I get to evaluate it at 0, simplify and evaluate it at 0. And I get a sub 2 equals 1/2. The third derivative of our polynomial has to equal the third derivative of our function. That's how our method of approximation is working. So that means that I need to evaluate the third derivative at 0, and then the third derivative of p at 0 is 6a cubed, or 6a sub 3, and a sub 3 equals 0. Then the fourth derivative of our polynomial has to equal the fourth derivative of our function. So those fourth derivatives, 24a sub 4, has to equal the fourth derivative of this square root function. Evaluate them both at 0, and I get a sub 4 equals 1/8. So now I have all the coefficients for this fourth order Taylor polynomial, this polynomial that's going to approximate the function square root of 1 plus x squared. So let's create that. A sub 0 we said was 1. A sub 1 is 0, so plus 0. A sub 2 is down here, 1/2. And then a sub 3 is over here, that's 0. And then a sub 4 is negative 1/8. So to simplify, our polynomial is negative x to the 4th over 8 plus x squared over 2 plus 1. And I rearrange those terms just for fun. So I put in the original polynomial into y1, or excuse me, the original function into y1, and the approximate polynomial, or the approximation polynomial, the Taylor polynomial, into y2. And I can see a nice approximation around x equals 0, maybe negative 1 to 1 again, our interval of convergence possibly.